All right, so we're in section 2.4. So complex numbers, I want to start with a very simple equation. X squared plus 1 equals 0. Well, we don't, it's a nice equation. It's not complicated. We would think that something like this we should be able to solve fairly easily. But when we try to solve it, we get x squared equals -1, and x equals the square root of -1. And we know that we don't know of any numbers where you square them and you get a negative number. Well, mathematicians, when we have something like this, what happens is mathematicians say, well, what if we just say there is something like that? Let's just say there is something that we square it and we get -1. Well, we call that I. And we call that the name of that is the imaginary unit. I is the imaginary unit, and it has this particular property that I squared is -1. So interestingly, a little historical side note, interestingly, the square root of -1 did not come initially, at least formally, from trying to solve this equation. It turns out that there's in developing an equation similar to the quadratic formula for cubic polynomials, there's a formula that exists where you can plug the numbers into this equation and get the roots of a cubic polynomial by a formula. It turns out that for cubic polynomials with real roots, that intermediate calculations in this formula, like the quadratic formula, intermediate calculations have the square roots of negative quantities, even though the end result is a real number. So what mathematicians said was, well, if we're solving an equation that has all real roots, and in the middle of it we get a square root of a negative something, that square root of a negative something has to be something that we can work with. Because we're getting a real result as an answer. So that's where the idea of square root of -1 equals I comes from. It comes from solving cubic equations. So what we're going to do today is just talk about some properties of complex numbers, and we will not have to use trig form. I know that's going to make all of you very sad. So complex number is our complex unit, imaginary unit is I, a number in the form a plus bi, where a and b are real numbers. We call this, stop talking please. We call this a complex number. So an imaginary number is just with an I. Complex number, we have an a plus bi, where a and b are real numbers. And we talked about these complex numbers a little bit before. And this is called in standard form. The a we call the real part, and the bi part we call the imaginary part. And I think I talked about this before. It's unfortunate that they call them imaginary numbers, but it's not imaginary in the sense that they don't exist. It's imaginary in the sense that the other numbers that mathematicians worked with then were called real numbers. So we had the real numbers, so these are not real numbers, so they were called imaginary numbers. Doesn't mean they don't exist. What's that? No, I think like Joe numbers. You could call them anything. Yeah. We could have the Aiden numbers. Aiden numbers. All right, so what we're interested in today is properties of these complex numbers. A plus BI equals C plus DI. Complex numbers are equal only if A equals C and B equals D. So we're saying the real parts are equal and the imaginary parts are equal. So that's how we know when complex numbers are equal. The real parts have to be equal, the imaginary parts have to be equal. To add or subtract complex numbers, A plus or minus BI, not plus or minus, A plus BI plus or minus C plus DI. That's where I want the plus or minus. Equals A plus or minus C plus B plus or minus D. I. So what we're saying is we add or subtract the real parts and add or subtract the imaginary parts. Hello.
Hi. Can I borrow Aiden for a yearbook interview?
Yes, we can. Ask him to tell you about Aiden numbers. Okay. So, for example, 5 minus 3i.
Hi, could I grab Max Rosenboom for an interview?
Yes.
Max, you're getting interviewed. You're a celebrity. Get it big. Max, you want me to go for you? No.
All right, so if we wanted to subtract 5 minus 3i minus 4 minus 4i, we're going to subtract the real parts. 5 minus 4 is 1. The imaginary parts, negative 3 minus negative 4. So negative 3 plus 4 plus 1i. Adding or subtracting complex numbers is, I think of combining like terms. All right, we good there? A plus BI times C plus DI. Do you remember what we have to do for multiplication? We have to distribute. And the acronym that we have for distribution in this situation is FOIL. So let's take a look at one of those. To multiply complex numbers, we just FOIL. So I'm going to say, let's say we have 2 minus 3i times 4 plus 2i. So we're going to multiply this out. Our first, we get 8. Outside, we get 4i. Inside, we get negative 12i. And for my last, I get negative 6i squared. And now I'm going to say this is 8, negative 12i plus 4i plus 8i. And then I squared is negative 1, so that's going to be plus 6. So it's 14 plus 8i. Minus? Oh, the 12 is negative. Thank you. All right, we good on multiplication? Hopefully this is review. All right, before we talk about division, we need to talk about the complex conjugate. So if we have a plus bi, the complex conjugate, do you remember how to get the complex conjugate? Something like, I think you were thinking of division already. The complex conjugate is a minus bi. We change the sign on the imaginary part. And we need the complex conjugate to do division. So a plus bi divided by c plus di. To divide. I think this is what you were thinking of, Gabby. We multiply the numerator times the conjugate, the numerator and denominator, by the conjugate of the denominator. So nice things happen when we multiply by the conjugate of when we multiply a complex number by its conjugate. So let's look at an example of doing division. Now, let's do the example first. Let's say 3 plus 2i divided by 1 minus 3i. So to do this division, we're going to multiply by 1 plus 3i over 1 plus 3i. I'm going to put my parentheses there so I distribute correctly. And now we just have a big multiplication problem. So we're going to do this numerator. We get 3 plus 9i plus 2i plus 6i squared. And in the denominator, I get a plus 3i, a minus 3i. So those go away. And I get a minus 9i squared. Well, this is going to be 3 plus 11i minus 6. Because I squared is negative 1. And this is going to be 1, I squared is negative 1. 1 plus 9 is 10. When I multiply a complex number by its conjugate, I get a real number. That's the nice thing that happens. So now we're going to simplify this. 3 minus 6 is negative 3 plus 11i over 10. If you wrote your answer like this, I would be fine with it. But technically, to be in standard form, we need to write it like this. This technically is standard form. So if the problem says write it in standard form, that would technically be standard form. I'm fine with it written like this. But just to be aware that if you look at the answer in the book, it's going to look like this. So before we talk about our last thing, why are we talking about complex numbers today?
Complex numbers and
You get like an x squared plus 1.
yeah, you can get conjugate.
Right, so there we go. for a quadratic polynomial, right? When we use a quadratic formula, we can get complex roots. So we need to talk about complex numbers. So what we're going to do next when we go on is we're not just going to find the real roots of our polynomial. Folks, stop talking, please.
Yeah, shut up.
So we're not only going to be looking at the real roots of our polynomials, we're going to be looking for the complex roots as well. So now, why did the mathematical tree fall over?
Why?
It had no real roots.
What about the imaginary roots?
No, that
It's not an imaginary root.
right. It's
Numbers are real numbers. You said that earlier. So if you did have roots, you would
no. Imaginary numbers are not real. Real numbers are complex numbers, but they are numbers. All right. Last thing we need to talk about is the principal square root. The principal square root, folks, principal square root is a convention that we're going to use. So mathematicians have agreed, and when we do things this way, things work out the way we expect them to. It's a way that we're going to agree to take the square root of a negative number. Square root of negative a, where a is a real number. Equals the square root of negative 1 times a. That's how we're going to agree to take the square root of a negative number. And the square root of negative 1 is I times the square root of a. So by convention, this is how we're going to take the square roots of negative numbers. Be aware that in your book, they write this as square root of a times I. And it can be difficult to tell if they mean for the I to be under the square root. In this chapter, the I is not under the square root. I always write it like this, so you don't confuse it. But in your book, it will write it like this. So we won't have to take the square root of I. We know, folks, we know how to take the square root of I, right? We'd write it in trig form, and then use that nice formula we had, cosine of theta plus 360k divided by 2 sine da 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 360k. We all remember that? Yeah? Isn't that so much more exciting than doing division this way? This seems so boring and mundane.
I like this way.
Yeah, the trig form is so nice.
No, I disagree with that statement.
All right. All right, folks. Let's look at an example, and I want to explain why we use this as a convention. Square root of negative 6 times the square root of negative 8. All right, ladies and gentlemen, please, let's stop talking. We're going to say this is I times the square root of 6 times I times the square root of 8. That's how we're going to take our principal square roots. And I squared is negative 1. So that's going to be negative square root of 6 times the square root of 8, which is negative square root of 48. And how do we simplify 48? 48 is 16 times 3. 4 square root 3. Now I'm going to write down here incorrect. If we did not use this idea of taking the principal square root, if we did not use this convention, we might just say, well, the square root of negative 6 times the square root of 8 is the square root of negative 6 times negative 8, which is just the square root of 48. which is positive 4 square root 3. And if we do things this way, then down the road, the answers that we expect don't come out the way we expect them. If we do it this way, then the math turns out the way we expect it to. All right, questions? Yes. You write I in trig form, and then use the inverse of de Moivre's theorem. We did that last semester.
Oh, so we don't have to do it this semester?
No, because technically we haven't learned that yet. Because this is in chapter 2 and we did that in chapter 8.
Oh, okay, cool.
But, yeah, we're going back in time. But, if you want to, you can. It's because it's so nice.
So like,
Yeah.
I went to a person.
You're hurting math's feelings.
Wait, there's another page. I thought there wasn't 90 to do up.
No, 93 on 5 every other option.
What does that mean?
Wait a minute.
90
to 105 every other eye. Oh no.